Hi everyone, welcome to another video for Reproducible Rehabilitation Research Education Program, or Repro Rehab. In today's video we're going to be talking about using tidy data to kind of reformat our data slightly and get it into really customized formats that allow us to create really helpful data visualizations. So the focus is going to be on visualizing a lot of the data that we've worked with in previous modules, where we were first merging and combining individual subject files to make one master data set, doing the heavier work of wrangling the data into a tidy data format. And now that we have tidy data, we can do smaller data tidying steps to kind of reshape the data into the format we want, calculate some new variables, and generally do smaller data management work compared to what we were doing in the data wrangling steps before. And you'll see the value of having gotten our data into that tidy format, because it's going to make it really easy to reshape the data and do the calculations that we need to do in order to create some really informative data visualizations. So go back and watch those previous videos if you haven't already. Hopefully you're kind of going through these things in order. But in this video, we're going to be building on the processed data set that we used or that we created in the last video on data wrangling. So the first thing that we're going to do, as always with these videos, is open the Tidyverse library and into our current session. Then we are going to set our working directory to the Repro Rehab folder within GitHub. So if you've cloned this to your local machine, you're going to want to navigate to that working directory. We can use the list.files function to look inside that folder, and we should see our three usual suspects there: the data subfolder, the README for the repository, and the scripts subfolder. Let's go ahead then and look inside of the data subfolder of the repository, and you should see this data processed eeg.csv file, which we created in the last video. We had our integrated master file where we had merged everything together, but then we went through some data wrangling procedures to calculate new variables, filter out things we didn't want, and ultimately end up with this processed EEG data file, which is in a very tidy format, and that's what we're going to work with today. So on line 9 of this script, we're going to import that data using the read.csv function. You can see that we've got 2,640 observations with 13 different variables. If we use the head function, hopefully you're getting pretty used to this now, right? We can take a peek at the first few rows of the data. We can see all of our different columns. So we have this variable X, which is just a row indicator. We have a subject ID. We have the condition, whether it was the eyes open or the eyes closed condition. And then for each subject, right, we're looking at the power spectrum of the EEG signal. So at each frequency, which is given by the Hertz column, we then have the power at the frontal electrodes on average, the central electrodes on average, parietal electrodes on average, and the occipital electrodes on average. And then we also have the log transformations of each of those respective variables. So this is pretty great, but if we click on the data here to kind of get a tabular representation of it inside of RStudio, you can see it's a really big, long data file, right? We've got unique observations for each person at each Hertz, which then leaves us with 2,640 rows, because we've got approximately 30 Hertz in each condition, 2 conditions thereabouts for each person. I think we have some people who are missing some data, and about 44 people. Right, so this is a big, long data file, and if we actually want to get some meaningful plots, it's going to be a little bit tough, because I might only want to look at the eyes closed condition, or I might want to look at on average across participants, right? So there's a lot of different ways we might want to look at this data, and the data aren't going to be in the right format for each type of visualization we might want to make. However, we've done the hard work in our previous videos of getting these data into a tidy format, which is going to make it easier to work with, and we can do a little bit further data management in order to reshape the data into precisely what we want. So that's what we're going to do first. Is we're going to aggregate the data across participants in order to get a grand average calculation. So to do that, we're going to use the group by function. So again, if we want to look at what group by actually does, we can put a question mark before the function in order to pull up the help documentation over here. And so group by allows you to group your calculations by one or more variables. In this case, we're going to group the operations by the frequency variable Hertz. So what we'll do is we'll push the data through a pipe into the select function. We'll drop that X variable off of the data. Then we will push that through the pipe into the group by function, where we will group it by hertz. And then we'll push that through a pipe into the summarize function, where we're going to calculate a variable called frontal mean, which is going to be the mean of the frontal electrode column. So if I do that, you can see it creates this tibble, and it's only going to push the first 10 or so rows to the screen here. But we've lost all the information about what subject it is. We've lost all the information about what condition it is, because now we are just creating at this hertz, right, at basically the less than 1 hertz, less than 2 hertz, less than 3 hertz, this is the power across, on average, across all participants and all conditions. This was the power on average across all participants and all conditions. So by summarizing the data in this way, grouping it by frequency, and then calculating the mean of the frontal electrodes, I can get like grand average mean power at each frequency. So that's going to be pretty helpful. We're not actually going to save that data yet, though, because what we might want to do is get summaries of all of our different regions. And to do that, we can use this summarize at function. So again, I'll say question mark summarize at. And you can see that this allows us to summarize multiple columns. Scoped verbs if, at, and all have been superseded by the use of a cross in an existing verb. So it looks like this is actually a slightly older term. They've updated the dplyr package to now instead use the term across rather than summarize at, but it looks like summarize at will still work. It's just superseded by this newer variable. So if I'll have to get myself up to date and actually look into using across at some time in the future. But let's go ahead and keep using summarize at, because that's still going to work, and that's going to affect variables selected with the character, vector, or vars argument. And so what we can do then is the same thing as before. This time we're going to create a new object, which we'll call data, or dat grand av for the data grand average. We'll take our data, push it through a pipe into the select function, drop the X variable, push that through a pipe into the group by function to group by hertz. So we're going to carry out the next calculations at each frequency. And then we'll push that through a pipe into the summarize at function, which will allow us to take a summary across multiple columns of variables. And in this case, I'm going to say frontal : ln occipital, because I want it to take the mean at each of these columns. So it's just going to go from frontal all the way through to our final column, which is ln occipital. And if I do that, now I can look at the head of that variable, right? You can see, okay, I've got my hertz column. I've got mean frontal power now, mean central power, mean parietal, and mean occipital power. Then I also have the mean of the log hertz, mean of log frontal, mean of log central, mean of log parietal, right? I could have done these means all separately within the summarize function, but the nice thing about the summarize at function is it allows me to get the mean at each of these columns with a lot fewer lines of code. So it's just going to be much more efficient if I know how to use that function in order to get what I want. So now, to get a little bit better handle on what these data actually look like, we can plot these grand average power spectrum data. So I'm going to walk through the ggplot code that we have here in order to do that. And I'm going to talk you through the different elements of this ggplot code a lot in this first example. And then in subsequent examples, we're going to try to just add a few things here or there. And I'll talk about some of the new stuff in ggplot, but we're really going to focus on kind of the foundational stuff here. So the first thing when we're creating this plot is that we have to tell the plot function where we're going to pull the data from. So we say data equals dat underscore grand underscore av, and then we can specify some aesthetics. And if I specify the aesthetics in the first part of this function, it's going to apply those aesthetics to everything else in the plot. I can also specify aesthetics in each individual plot component if I want slightly different aesthetics. But if I specify the aesthetics with this AES function inside of the ggplot argument, then it's going to default to those things on all of the subsequent lines. So the aesthetics that I'm going to set for everything else are that my x-axis is going to be hertz, and my y-axis is going to be the frontal column of my grand average mean data. So let's go ahead and run this whole thing so you can kind of get a look at what it produces, and then I will talk through what each of these elements is doing and how it shows up on this plot. And the first thing to understand with ggplot is that the name is short for the grammar of graphics, right? So it's the grammar of graphics plotting tool. And the nice thing about this is that ggplot allows you to basically say and. So you can set some base conditions for your plot. Then I have this little plus sign that is grammatically like an and. So, and I want it to have a line drawn on this graph. So it has these geomes, which are geometric primitive objects, or geomes. So geome line basically allows us to draw a line, and it can take a lot of different arguments. But right now I'm just saying color equals black. So I'm accepting all of the other defaults, and I'm just saying that I want this line to be black. And that geome line argument, or that geome line function, is ultimately drawing this black line, showing the relationship between power and frequency on average across all of my data. Then I have a plus sign again, so I have another and. So this is going to add a layer to my plot. And on top of that line, I also want some points. So I can use the geome point function. And again, geome point takes a lot of different arguments, but I'm only going to specify 2 and accept the defaults on everything else. So I'm going to say shape equals 16, which is a solid filled dot in R. So that if I say shape equals 16, that's going to give me a dot of a fixed color. And then I'm going to tell it that I want that color to be black. And so that's going to give me these black dots on top of my black lines. Next, I can specify some things related to the x and y axes. So I have 2 continuous variables, so I'm going to say scale x continuous. And again, there are different things you can set within this function, such as the limits of the axis. But the only argument I'm going to set is that I want the name equal to frequency with hertz in parentheses. So when I specify that, that's setting frequency, and then hertz in parentheses down here as the name of my x-axis. It's drawing the limits by default based on the data that we have. But if I wanted to, I can actually go into this function here and add a limits argument to customize what limits I want the plot to show. Similarly, for scale y continuous, right, the only thing I'm specifying is that this is power, and this is power in the frontal region, but I'm actually going to specify that in the plot title. So I'm just going to label the y-axis as power. Power, you wouldn't know this from the data, but in the data dictionary for these data, they are in microvolts squared. So this is in units of microvolts squared on the y-axis. And you can see then we've got this big fall off over time where we have a lot more power in our signal at low frequencies and a lot less power in the signal at high frequencies. But this is what the grand average power spectral density looks like for the frontal electrodes during this study. So next, I have this GG title, where again, this is adding a layer to my graphic, right? Every time I have this plus sign, it's like I'm saying and. So I've set my axes, I've set my points and my lines, and now I'm saying and put a title on here. So I'm just going to say GG title is frontal power, and that's going to draw this part of the plot up here. Now, down below that, I've got some things about the theme and then specifying some other aesthetics about how I want the text and the font to show up. But what I'm going to do is actually just delete this plus from the end of line 34 after GG title. And then I am going to comment out these lines for right now to basically show you what this plot would look like if I turn off the theme and I turn off everything else that I'm specifying. So now you can see I've drawn this to have basically the same structure, right? I've still got frequency on the x-axis, power on the y-axis. I'm showing you the average power spectral density across the frontal electrodes. But you can see a lot of the aesthetic features have changed. My title is no longer, centered. It's over on the left-hand side. The background fill of my plot is gray. My axis values and my axis labels are no longer the same size, right? And they're not bolded. So a lot of things have changed in the cosmetic features of this graph. So that is, kind of to show you the basic plotting principles and what you would get by default out of ggplot. Now, there are a lot of different things you could set with respect to theme. So theme black and white, or theme BW, which I will turn on here, changes some presets. So by default, ggplot uses a gray background and it has the theme gray. But what I actually like is, kind of a black and white plot most of the time, especially if I'm submitting something to like a print journal for publication. So I like to use theme black and white, but you could use theme, classic is another theme that's available where those tick marks are actually now removed. You could set this back to theme gray, which is the default. And then there are other packages that allow you to set a whole bunch of different themes, including like dark themes. If you want something to have a black background, maybe in a slide presentation where you're actually presenting with, color figures or white lines on black, you can have a lot of fun playing around with different themes. You can even create and build your own themes. But I like theme black and white, so I'm going to set theme black and white here. Now, after theme black and white, I can customize a lot of stuff within the theme. So by setting theme black and white, a lot of these theme arguments have certain defaults, and that is what theme black and white is changing. By doing theme black and white and then adding my own theme argument, I'm going to supersede some of the defaults within the black and white theme. So for instance, for my axis text, I want it to be 10-point font, and I'd like the color to be black rather than this kind of gray that it's defaulted to here. If I had a legend, I'm currently not actually, I don't have anything in a legend right now, but I can control how big I want the text to be, what color I want the text to be. For my legend title, right, I can set, what size I want that text to be. Do I want it to be boldface or italic? Similarly, for my axis titles, I want them to be a little bit bigger than the axis text, right? So axis.text controls the axis text. Axis.title is controlling the axis title. So I want these to be size 12 rather than size 10, and I'm setting them to bold, right? Then on my plot title, I'm setting that to size 12. I'm setting it to bold, and then I'm also using the horizontal justification of 0.5 to center this title. So at the moment, right, when I had these arguments turned off, frontal power is bigger than 12 point and it's left justified. I want to scale this down a little bit to be 12 point, bold, and centered. So that's what I'm setting here. It's going to be 12 point, it's going to be bold, and it's going to be centered. Then I can turn off things like minor tick marks within the panel. I can control strip text, which we don't actually have in this figure, but that's going to show up a bit later on. So this argument will probably make a bit more sense in some of our later figures. And then in this one, we don't actually have a legend because, again, we don't have any lines grouped by condition or grouped by subject or anything like that. So there is no legend to actually display in this graph. But if I was to have a legend, I'm currently drawing it to go at the bottom. So now that I've turned on all those theme arguments again, let's replot our data. Okay, and then we get a plot that looks like this. And so we've specified a lot of things cosmetically based on what I like, but I would encourage you to go around, look at the different themes that are available, maybe play around with some of these arguments in here, and then you could even customize your own theme and save it to be theme _ your name, and then you wouldn't have to have this big long set of arguments here. You could just specify your favorite theme, and then that's all you have to do in order to set that up with your plot. In the next plot we're going to create on line 46, we're going to do exactly the same thing, but now we're going to work with the log transformed version of our variables because, again, you can see we have this really strong skew in the power variable. And at low frequencies, we have really high power that falls off a lot as time goes on. So if we actually want to get a better kind of visual depiction of this, we might want to plot this in log-log space, where we take both the log of power and the log of frequency, and we're going to plot log transformed power against log transformed frequency. We get to see this nice exponential decay function when we plot it in the raw space, but in log-log space, we're actually going to see some variations. You know, you can see this little bump down here at this higher frequency now that we were missing before. And this is because obviously when we went back to the previous scale, right, this variation around 10 hertz is just way smaller than the absolute power at the low frequency. When I put that into log-log space now, though, that little bump is actually a lot more visible. And so depending on what I'm trying to show to my audience, this might be a better way of looking at the data. We're going to play around a little bit with looking at it in both raw space and log-log space, but the log-log space is going to be really helpful for us moving forward. Okay, so next we might want to actually get a more detailed plot, because right now I'm just looking at frontal power. What about power in the central, parietal, and occipital regions? Well, we're not going to have that in an easy format the way the data are currently structured, because frontal, central, parietal, and occipital are all set up as separate variables. In reality, though, frontal, central, parietal, and occipital are not the best names kind of for these columns, because we're conflating two different variables when we put these into wide format and we have multiple columns for each of these regions. In reality, what each of these columns is showing is power, but the power varies by region. So what we're going to do is actually reshape the data in order to get one column, which is power, and another column, which is region. So we're going to transform these data from long to wide format. So to do that, I'm going to take my data grand average. I'm going to push it through the pipe to select everything from hertz to the occipital columns. And then I'm going to push that through a pipe into the pivot longer function. And what pivot longer will do is transform these data from 4 different columns into 2 columns. So basically at 0.997 hertz, what we actually have are 4 different observations. We've got a frontal observation, a central observation, a parietal observation, and an occipital observation. So now, rather than 1 row with 4 columns, we're going to have 4 rows at 0.997 hertz. And then we'll have a new column, which actually tells us the power in each of those rows. So that's what we're going to do when we take names 2. We're telling it, take these columns, put them in a new column called region, and put their values in a new column called power. And if I do that, we can now look at the head of the grand average long data set. And you can see we've pivoted this from a wide format where we had lots of columns into a longer format where we have lots of rows. And now at 0.997 hertz, we actually have 4 different observations, right? We have the frontal, central, parietal, and occipital observations, and then we have 1 column which is power. On line 70, we're going to do the same thing, but this is with the log transformed data. So the code is exactly the same. I'm pushing the grand average data through the select function, but now I'm taking the log hertz to log occipital, then I'm pushing that through pivot longer. I'm going to tell it that I want to transform the columns, log frontal to log occipital, names to region, values to log power now rather than just power by itself. And if I do that, oops, this should be data grand average log. You can see, okay, this was, 0.99 hertz in the raw space. It's negative 0.03 log transformed, but I've got frontal, central, parietal, and occipital regions, and then the log power in each of those regions. So now I can actually plot these data. So my basic data structure is going to be the same, my basic ggplot structure is going to be the same as it was before. But now, rather than pulling from the grand average data, I want to pull from the grand average long data set. Hertz is still going to be on the x-axis, power is still going to be on the y-axis, but now inside of my geom line, I'm going to specify the aesthetic that color is equal to region, and inside of my geom point argument, I'm going to specify the aesthetic that color is equal to region. And remember that region is this new variable in my long format data set. So let's go ahead and put that on the screen. And now you can see by specifying these aesthetics within the geom line argument and the geom point, the geom line function and the geom point function, I get different lines color-coded by what region it is, and different sets of points color-coded by what region it is. And now I actually have a legend, right? So it's going to show up on the bottom of my plot because I specified legend position equals bottom. I could also say legend position equals right if I wanted it to be on the right, or legend position equals top if I wanted it to be on the top. But in general, I think like having your legend on the bottom of your graph looks pretty good. So now we can see that, nice exponential decay, but how it's a little bit different in each of those regions, with the largest amount of power actually being observed in the occipital region. If we want to do the same thing, but in log space, right, all I'm going to do is change the data input to the grand average log data set. And now my x is equal to the log of hertz, and my y is equal to the log of power. But otherwise, everything else is going to be the same, because I still want it to draw lines for different colors based on the region, and I still want it to draw points of different colors based on the region. And if I do that, now we can actually see that nice little bump in the data at around 10 hertz, and how that is attenuated depending on what condition we're in. And specifically, the occipital and the parietal regions tend to show the biggest bump here, whereas the central and the frontal regions show a little bit smaller bump. So that allows us to visualize our data within the different regions of the scalp that we're looking at. But remember, we also have data collected in eyes closed and eyes open conditions. So maybe rather than taking grand average data where I get the average at each frequency, what I would really want is the average at each frequency in each condition. So I'm still going to average across subjects, but what I want to be able to see is the difference between the eyes open and the eyes closed condition. So let's go back to our original data set, the data, and I'm going to create something called dat_cond_av, right, or the data condition average, by taking data, passing it through the group by function, and now I'm going to group by both condition and hertz. So it's going to look at eyes open, hertz 0.997, eyes closed, hertz 0.997. And then I want to get the same summaries as before, so I can get the mean power in each condition at each frequency. So I'm still going to average across subjects, but now I will get a unique observation for my eyes closed data. And then, it's not showing it because it's not printing all the rows to the screen, right? But I also have the average in the eyes open data as well. Then we can do the same thing we did before to pivot this longer, because again, I'm going to want to be able to visualize these different regions. And to do that, I need a region variable in my data. So I'm going to push my conditioned average through the select function to take the columns condition to occipital, right? So that's condition to occipital. Then I'm going to push that through the pivot longer function. And the columns I want to pivot are the frontal to occipital columns. Those are now going to all go to a new variable called region, and their values are going to go to a new variable called power. And if I do that, you can see now in this dat condition long format, I have a condition variable. So I've got eyes closed and eyes open. My hertz variable, right, where I have 4 observations at 0.997 hertz in the eyes closed condition, because I have one unique observation now for frontal, central, parietal, and occipital. And then at the next hertz, I also have one observation for frontal, central, parietal, and occipital. But this is a long format data set that's going to allow me to get a plot like we had before, but now I can look at it in both the eyes open and the eyes closed condition. If I also want that again for log power, I'm going to do the same thing. I'm going to pass my conditioned average into the select function, but now I will take the condition column And then I will also take log hertz to log occipital. Right, so again, I'm passing in this data set, the DAT cond av. I want to keep condition because I want that information in there. But then I'm going to skip over these raw columns to only take the log transformed columns. So I'm going to take log hertz to log occipital, and then I'm going to push that into the pivot longer function. The columns I want to pivot are log frontal to log occipital, and then I'm going to put all those names into a new variable called region and put all their values into a new variable called power. And if I do that, I can look at the head of this DAT cond long log transformed data set. You can see again, I've got my condition variable, my hertz variable, my region variable, and then I get 4 observations for every hertz in every condition, and I get the power corresponding to that hertz in the different regions. So now, equipped with these long format condition data, I can actually draw a new plot. So we're going to set this up much the same way we did before, right? We're kind of adding things a little bit at a time here, where we're saying data is equal to dat cond long. So this is the raw data, but in the long format with averages for each condition. X is still hertz and Y is still power. We're going to color code our lines by region, and we're going to color code our points by region. But now we're going to add this new function where we say facet wrap tilde condition. And what facet wrap allows you to do is to create different facets of plots. Let's go ahead and run this code on line 128 so that you can see that, and it'll make a little bit more sense. But now you can see inside my plot window, I have 2 facets, or sort of mini plots. I have one for the eyes closed condition and one for the eyes open condition. And you can see we get very different looking average power spectra in each of those conditions, especially for the occipital lobe. We have much higher power in the eyes closed condition and much lower power in the eyes open condition at those low frequencies for the occipital lobe. Now, this facet wrap argument then is taking our data and spreading it out between those 2 different facets, right? So we have region information, hertz information, and power information in each condition. So in this data long data set, right, I basically have duplicates of all of this stuff. I have it in eyes closed and I have it in eyes open. So facet wrap is making sure we don't duplicate that information on the same plot, because if I turn that off, for instance, by commenting out the facet wrap argument, our plot's going to look really weird, and we get these kind of like little buzzsaw looking things where there's weird edges connecting different lines. That's because, right, at 0.99 hertz, I have 2 observations. I have an eyes closed observation and an eyes open observation. Similarly, at 1.99 hertz, I have an eyes closed and an eyes open observation. So now geome point is drawing both of those points, and geome line is connecting both of those points. But that's not actually what we want, because I have those points are in 2 different conditions. So I would either need to specify that within like the geome line argument to draw 2 different lines for each condition. But then my plot's going to get really busy. So let's just do it with a facet wrap to effectively create 2 different plots where I can show the lines for each region in each condition over here. And again, given the skew in the power spectrum, it's going to be really helpful most of the time to look at this in log-log space rather than in the raw space. And if we do that, now you can see again that bump that was around 10 hertz, right, is very different in the eyes closed condition relative to the eyes open condition. This is an attenuation of what we would call alpha power in the EEG signal, because alpha is an oscillation between about 8 to 12 hertz, and usually it indicates when the cortex is kind of at rest. So when your eyes are closed, especially in your occipital lobe, which is responsible for your visual processing, we'd expect alpha power to increase. This is essentially like the idling frequency of your cortex. So you're not getting visual input, so alpha powers we expect to be higher in the eyes closed condition compared to the eyes open condition, and that's precisely what we see here. If we wanted to take these plots a step further to get a little bit more information, we can create what we would call spaghetti plots, where we're actually going to draw individual participant data and then maybe layer kind of group level data over the top of it. So on line 166, that's what we're actually going to do. We're going to take our raw data, and rather than getting an average for each condition, like we already did with the DAT cond AV, we might want to take this a step further and actually plot individual participant data. But one of the things that we might see is that when we plot individual participant data, it's going to get really noisy. So this average level data is still going to be really helpful to us, and we can create two different layers to our plot now in ggplot by specifying one geome line that goes with the subject data and another geome line that goes with this group average data. So that's what we're doing with the plot on line 170. So let me go ahead and create that plot, and then I'm going to talk you through what the different parts of the code are doing in order to create these nice plots. So you can see we've got a pretty colorful graph over here now, where we've got our eyes closed data and our eyes open data. We've got the power on the y-axis. I should say this is log transformed power on the y-axis and log transformed frequency on the x-axis. I'm going to need to update those labels. We'll do that in a second. But we have colorful individual thin traces, right, for our individual subjects. And then over the top of that, we are drawing the group mean average as a thicker black line. So this kind of, what we call it a spaghetti plot, right, because these are like little strands of spaghetti. But this kind of spaghetti plot is really helpful for showing both the central tendency in your data by showing the condition average as the black line, and for showing the individual variability in your data, because I'm showing you literally every power spectrum for every individual. So I'm being pretty transparent and upfront about just how noisy some of these data are, right? We have some people who have very high power at these high frequencies, and there's a lot of individual differences, both in the size of these peaks, right? Compare, for instance, this purple individual here to this kind of cyan colored individual down here. One shows very little alpha bump, one shows a really big alpha bump, and also where those peaks are centered. So some people show an alpha bump much earlier in time, whereas other people show an alpha bump much later in time. So the spaghetti plots are really informative and I think a useful way of presenting these kinds of data. So let's take a little bit deeper dive into the ggplot code to understand how we're creating it. So first, in terms of our the data in the first ggplot function, we're going to call our subject level data. So that is this one where we say head data, where every subject has a unique observation at each frequency. On the x-axis, we're going to plot our log hertz. On the y-axis, we're going to plot the log of the occipital power. And then we're going to draw a geome line. So we're going to draw a line for each person. We're not drawing any points now. We've dropped the geome point argument from this code. But for our first geome line, we're going to group, we're going to set our own aesthetics, where we group the lines by subject ID, and then we're also going to color code the lines by subject ID. So I don't necessarily need to color code those lines. I could turn off this argument, right, and specify a separate color. So I could say, for instance, color equals gray here. Oh, whoops, and I need to put a comma in there. And now if I set, if I no longer color them based on the subject ID, and I just say the color for all of these individual subject lines is gray, you can see my spaghetti plot looks a lot different. I still see those individual traces for each subject. It's a lot less colorful, and it's a little harder to tell which subject is which. So if I was trying to do something, for a print journal where it has to be black and white, this is still really helpful for showing the variability in the data. But if I'm doing something online or for a presentation, it's probably going to be helpful to say color equals subject ID and keep that more colorful version of my plot, where it's a little easier to show what data really belong to what subject. Then I'm going to facet wrap as we did before, right, in order to show two different plots for my two different conditions. And then I'm going to have a second geome line function. So this is new to us, right? We haven't done this yet, but what I can actually do in ggplot is add another layer that has another line. This is the beauty of the grammar of graphics. It's really easy to add new things into the sentence, right, of your figure. So within this geome line function, I no longer want to call the individual subject data. So I'll say data equals dat_cond_av to get those condition average data. But my x and my y axes are the same thing. And this is going to be important because you generally want these things to have the same name between your two different data sets. They don't necessarily have to have the same name, but giving them the same name can make it a little bit easier to make sure that you're drawing the right thing the way that you think it is. So from our conditioned average data set, I do want the x-axis to be the log of hertz, and I do want the y-axis to be the log of the power in the occipital region. So by doing that now, setting color equal to black and line width equal to 1, that's actually going to draw this plot where I have my individual subject data from my first geome line, and then I have my conditioned average data from my second geome line drawn as these thicker black curves that run over the top of the data. If I wanted to change some things about that, right, I could, for instance, make them thicker by changing this line width argument from 1 to 2. And that maybe looks a little too chunky, right, a little too cartoonish, but it depends on what you need and how visible you want those data to be. I think a line width of 1 is probably pretty good in order to show that. If I did want to change these lines a little bit more, I could, for instance, add something in the aesthetics where I could specify line type by saying LTY, and I could say LTY equals condition. And now if I do that, oh, whoops, I need to spell condition correctly. You can see it's going to draw a different line type in each of my two different plots. So I've got a solid line for the eyes closed condition and a dashed line for the eyes open condition, because it defaults to the solid line will be the first observation, the dashed line will be the second observation. I think then it would go to a dotted line theoretically for like a third level if we had it. But I could add things like line type here in order to make those lines really visually more different and more distinct. However, since I'm already plotting these things in different labeled facets, I don't really know that I need that, so I'm gonna change that back to just be solid lines in both panels. The one thing I did notice, however, was this is log power and this is log frequency, so I should probably specify that this is in fact the natural log of hertz, and this is the natural log of the microvolts squared. So I can change those units inside of the name, right, of this function. And now I get slightly more accurate labels here when I'm plotting these data. Okay, so one more added wrinkle that we have here is that not only do we have eyes closed and eyes open data, it's important to remember that those are actually from within the same subject, right? So this purple line over here has a corresponding purple line over here in the eyes open condition. Our plot doesn't really convey that at the moment because we're just seeing, the variability between subjects over here and the variability between subjects over here. So one of the things that we might really be interested in doing is trying to look at the difference in this alpha bump within the same person, right? Because how much the alpha bump changes is going to depend on which person you are. And we see that this person shows a big alpha bump in the eyes closed condition, but do they also show a really big alpha bump in the eyes open condition? So because these data come from within the same subject, it might be really interesting to look at the difference between the eyes closed condition and the eyes open condition for the same person. So let's come back to the head of our data set because we're going to start working with this in order to do some transformations. So what we will want is to actually get our data from the same person onto different columns so that it can be a little bit easier to do the subtraction. And there are a lot of ways that you could do this, so I'm just going to show you one way to do this in reshaping the data. But ultimately what we're going to want to do is you can think about that subject 1 has an eyes closed observation at 0.97 hertz. They also have an eyes open observation at 0.997 hertz. What I would really like to do is get those observations in two different columns so that I can easily subtract one from the other. The other thing that we're going to want to do is take these subject IDs and extract one new piece of information. So we want to take the first part of this subject identification, whether it's an OA or a YA, and create a new variable which we will call group. So that's our older adults, right, and our younger adults. And the reason we actually want to do that is because a major hypothesis in this research for which these data were actually collected was that older adults should show less of an alpha change from eyes closed to eyes open conditions than younger adults. So, we're recording this EEG activity from the scalp, and as we mentioned briefly before, alpha activity in this region right here is sort of like the idling frequency of the brain. So when you're not getting visual input, we expect the occipital lobe to have relatively high alpha. When you open your eyes and suddenly you now have more visual input, we expect to see a bigger change in the brains of our younger adults. Essentially, they are responding to this visual input more actively, whereas in the older adults, we expect to see less of a change. They have less of an ability to modulate that alpha frequency, and their eyes open condition, we expect to look more like their eyes closed condition. So to do that, we're going to use that string subset argument that we've used before, right? Again, if you want to remember what it does, you can always use the question mark and then the name of the argument. And we are going to create a new variable called group, in which we use the string subset function to take the first two characters out of the subject ID. So we're going to push our data frame data through the mutate function to calculate a new variable called group, which is a subset of the string subject ID, and we're going to take the first two characters. We're then going to push that through the select function to take the columns of subject ID, condition, group, hertz, just the occipital power, and then log hertz and log occipital power. We could do this with all the different regions, again, if we really wanted to, but because our primary hypothesis was about the occipital cortex, we're going to focus on just the occipital cortex now when we look at these data. And then we're going to pivot this to be wider, and we're going to take the names from the condition column in order to spread that out into separate columns where we'll have values of occipital power in eyes open, occipital power in eyes closed, log occipital power in eyes open, and log occipital power in eyes closed. So let's go ahead and run that code on line 193 to take a look at the data. Whoops, and actually I'm going to do that again. And then I'm going to talk through the different parts of what we just did and kind of turn them on and off so you can get a better appreciation for what these different pieces are doing. So this is what we ultimately want our data to look like, right? So we've got our subject ID and our new group variable. So subject OA01 was in the older adult group. So that looks good. That's worked the way that we wanted it. We also have our hertz. So we've got 0.997, which corresponds to the log hertz of negative 0.003. And we only want one row, right, at each hertz for each subject. Because now, rather than having eyes closed and eyes open in separate rows, we have eyes closed power in one column and eyes open power in one column. And we have that for both the raw data here and then also the log transform data here. So we've successfully reshaped our data to now make it really easy to calculate a difference. Because if I want to get the difference in log power, I can just take this column, minus this column to calculate the difference. But let's take a step back to actually look at what the different parts of this code are doing. So I'm going to come back up to line 193 just after our mutate argument. I'm going to put this down a line and then insert a comment to basically turn off everything else down below. I'm going to break this chain of events and just look at what the mutate argument is doing. So if I just do that, let's look at head occipital wide. You can see now we pushed data into the mutate function to create a new variable called group, which is the result of the string subset function, where the string we're going to take is the subject ID number, and we're going to start with the first character and end with the second character. So by doing that and saving it as data occipital wide, this data frame, data occipital wide, now looks like this. It looks exactly like the original data, right? I start with that X variable, I've got subject, condition, all the different regions, and all I've done is create this new variable called group, which takes the values of the first 2 characters from the subject ID. So our older adults have OA, our younger adults have a YA. Okay, let's go ahead and turn on our first pipe, and now we'll turn off the second pipe. So now we're going to do the exact same thing. We're going to push the data through the mutate function to calculate that group variable, but then we're going to push that result into the select function in order to select just a couple of columns that we really want. And specifically, we'll take subject ID, we'll take condition, we'll take group, hertz, occipital, log hertz, and log occipital. Now if I do that, right, again, you can see we've broken the chain, so it's not going through this next pipe. Let's look at the head of the data occipital wide. Our data look really different, right? We've lost all of these other columns because we did not select them. And so now we have that group variable like we wanted, but you can see we still have condition in columns. So we're getting all of the data for the eyes closed condition first, and then we're going to get all of the data for the eyes open condition after that. And what we really want to do here is pivot these data from long format to wide format in order to do the calculation we want and get the visualization that we want. Sometimes you'll want to go from wide to long, sometimes you'll want to go from long to wide. It just depends on what you need the data to do, so being able to pivot between wider and longer data formats is a really helpful skill to have. And what we want to do here is, rather than have one occipital column and eyes closed and eyes open be in different rows, I'd like to have one column for occipital eyes open and one column for occipital eyes closed. So if we come back up here to line 194, remove the comment and turn this pipe back on, now we're connecting the whole chain, right, the way that we had it in the beginning. So again, we're going to push the data through the mutate function to calculate a new variable called group, which is the result of our string subsetting, where we're going to take the subject ID and we're going to take the first 2 characters from that subject ID. Then we're going to select just the few columns we want, which are the subject ID, the condition, the group, the hertz, occipital power, log hertz, and log occipital power. Then we're going to push that smaller data frame through a pipe again into the pivot wider function. So before we used pivot longer, now we're using pivot wider because we want to take something that's represented in rows and change it into columns, making our data wider. And specifically, we want to take the names for our new columns from what is currently the condition column. So it's going to take those EC and EO values and turn them from rows into columns. And the values we want to transform with this are specifically the occipital column. So we'll have an occipital EC and an occipital EO, and the log occipital column, so that we'll get a log occipital EC and a log occipital EO. And by doing that, right, and now looking at the head of the data, we've done all of the things that we want to do. We've got our new variable of group, so older adults are labeled OA, younger adults are labeled YA. We've got our hertz and our log hertz, and now we've got 2 columns for the occipital power, one for the EC condition, one for the EO condition, and 2 columns for log occipital power, one for the EC condition, one for the EO condition. And now that's going to make it really easy for us to calculate the difference within each person. So we're going to calculate a new variable called diff ln power, which is just the difference in the eyes closed condition, which is just the power in the eyes closed condition minus the power in the eyes open condition in order to get one different score for each person. And if we go back up and look at the head of our data now, you can see I have this new value called diff ln power, which is this condition, eyes closed, right, minus this condition, eyes open. And I'm going to get a different score at each hertz. If I now want to plot those differences, I can take my ggplot function. We're going to use our new data frame called data occipital wide, where x is the log hertz, y is the difference in log power, that new variable we just created, and we're going to draw lines for each subject. So let's go ahead and do that. So now you can see that we have a spaghetti plot where we've got lines for the difference now between our older adults on the left and our younger adults on the right. There's a lot of really noisy information, but we're really, again, interested in kind of what's happening in this alpha range here. And do the older adults show a bigger or smaller bump on average compared to the younger adults. So this is really helpful to see the variability in our data, and we can definitely see that there's, some evidence of around that kind of alpha point, there's more homogeneity in the responses, whereas at very low frequencies we see, just it's kind of all over the place, and at high frequencies it's a little more all over the place. Within that alpha region, there appears to be a more predictable behavior in the difference. But what we're really interested in is, do the younger adults show a bigger difference on average than the older adults? So in order to do that, we'd really like to plot the group mean differences. And we do have condition mean data from before, right? If we go back to line 205 and 206 and we turn on a new geom line argument, we can draw the condition average data, but there's going to be some problems with that because that's not actually what we want, right? If I look at like head dat underscore cond av, that isn't showing me differences. I don't have anything in this data set that shows me differences, which is also then why these lines look so funky, because what this is showing me is the actual average values for the older adult group and the younger adult, and actually in this, it's showing me the average values for the older adult group and the younger adult group, but I'm getting like doubled up here because I've got an eyes open and an eyes closed observation, so I'm getting these weird kind of jagged lines. So we have to actually now calculate some group mean differences, because although we had condition averages in our previous data, we did not have the average group mean difference. So let's actually do that calculation first to make sure we really get the plot that we want, and then I'm going to talk through what we're actually plotting in the ggplot code in a little bit more detail. Okay, so let's go to calculating the group mean differences. We've got our wide format occipital data, which we have here, where we have the data for each individual person and the difference in terms of log power. If I want to get something for the group mean differences, I'm going to call this data occipital wide group av on line 225. So it is a very long name for a data frame, but at least it's descriptive, so I can hopefully remember exactly which one I want here, because we're going to look at the occipital data in wide format for the group averages. And I'm going to take my wide format occipital data, I'm going to pass it through a pipe into the group by function, where I'm going to group it by group, right? So I want the older adults to be one group and the younger adults to be one group, and hertz, because what I would like to do is average across people to get the average difference for the older adults at 1 hertz and the average difference for the older adults at 2 hertz. So I'm going to group it by both age group and hertz, and then I'm going to pass that into the summarize function, where I'm really just want the log data right now, so I'm going to ignore the raw data altogether. And so I'm going to take log hertz, and it's just going to keep the first value from the log hertz, right? So when we're looking at 0.997, it's going to take negative 0.003. And when we're looking at 1.99, it's going to take 0.690. And then I'm also going to calculate a new variable called diff log power, and that's going to be the mean of the diff log power variable, right? Because I have a difference in log power for each person at each frequency. And what I really want to do is average across people to get the average difference in the older adult group at that frequency and the average difference in the younger adult group at that frequency. So let's go ahead and run this code on line 225. Let's take a look at our group level data set. And you can see now I've lost the information about individual subjects, and I now just have, for the older adults, one observation at 0.99 hertz. I have one observation at 2 hertz, one observation at 3 hertz, right? So I can actually look at the difference in power now between my different groups. So let's go ahead and do this ggplot, and then I'll talk through the different parts of it. Okay, so again, we're drawing a spaghetti plot here where on the y-axis we have power, and on the x-axis we have the frequency. But what we're actually plotting is the difference between the eyes open and the eyes closed conditions. So we're going to need to do some relabeling of our axes here, and we want to show that for both our older adult groups, right, in this facet, and the younger adult group in this facet over here. And showing the individual subject data is really helpful, right? Because it shows the variability in what we have. But we're also really interested in the mean differences. And specifically, we predicted that our younger adults were going to show a larger alpha modulation on average compared to our older adults. And it looks like that is correct. The older adults on average show less of a difference between the eyes closed and eyes open conditions compared to the younger adults, right? They have a bigger change, they have a bigger mean difference than the older adults do in that alpha range. So in order to get this plot, we're again layering two different data sets. We're starting with our wide format occipital data to draw the log frequency on the x-axis and the difference in log power on the y-axis. And then we're going to show that with a line where we're grouping these lines by the subject ID number, and we're going to give each subject a unique color. Then we're going to facet wrap those by age group, right? So that's drawing our two different panels here. And then we're going to add a new geome line that refers to an entirely different data set. And this is, again, the beauty of the grammar of graphics, is we can add these layers on top of each other in the same plot to get what we want. So our first layer referred to our subject level wide format data. Our second layer is going to refer to our group average wide format data, right? Where now I only have one observation for each group at each frequency. I still want to plot the same thing on the x and the y axis, right? But I want them to be a little bit thicker, and I want them to be solid black lines so that I can easily differentiate the mean difference for the older adult group from individual lines in the older adult group. And similarly, get the mean difference in the younger adult group separate from individual lines in the younger adult group. Now, I do want to update these labels a little bit because, first of all, rather than frequency, this is actually in log hertz. And then I should say this is maybe something like the change in log power. And I'll actually delete the units to maybe just say which direction this subtraction is going. And it was eyes closed minus eyes open, right? To make it clear then that if we have a positive value here, that means the power was higher in the eyes closed condition to the eyes open condition. If we have 0, that means the power was equal. And if it's negative, then that means the power was actually greater in the eyes open condition compared to the eyes closed condition. And if I run that code, now we actually get like some nicer labels that make a little bit more sense. We can see the spaghetti plot, which clearly shows us the individual variability in our data, but we also get some means that show us the average trends within that group for these EEG data. So in the subsequent video, we're going to get into a little bit more about statistical analysis and some basic approaches to stats with these data, and also some plots that are less about showing you the power spectral density, but maybe more about showing exactly, the mean at a certain point, and some box and scatter plots that you might be a little bit more used to. So stay tuned for the next video where we're going to go through some fundamentals of statistical analysis, and then also explore some other kinds of plots that maybe are a little more common when you're showing things like mean differences compared to these power spectral densities that are a little more common when you might be showing something like biosignal processing.